Welcome Grzegorz on Innovation Showcase Tech Talk. Grzegorz will tell about behavioral code analysis. Remember that after his talk you can vote on the tablet and the end of this room.
Thanks. Yeah, that's okay. So, while working here in Motorola for the past 11 years, I have seen at least several attempts to introduce static analysis to various projects. And many of these attempts were made with a goal of quantifying, assessing, and addressing technical debt. So I remember that one product where technical debt analysis was installed and executed, and it displayed this beautiful tree map of all the folders where the good quality code was marked in green color. And the bad quality code was marked with red. And upon looking at that, we knew straight away that we would not be able to fix everything, because that would have probably taken at least several years. So the big question became what to clean up first, and where could we get the biggest return of investment from our cleanup efforts? And at that time, I didn't really have a good answer to that question. But I believe I do now. So let me tell you about prioritizing technical debt using behavioral code analysis, which is an approach that was introduced by Adam Thornhill in his books, notably the Software Design X-Rays. And Adam's advice is to clean up the code where it will ease the future evolution of code base. But that's easier said than done, because we don't really know how the code will evolve, because we don't know the future. But maybe we can learn something from the past, from how the code has evolved. And as all of you know, the evolution of a code base is a dynamic process. This is not something you can present as a static picture, such as this one. But thankfully, we have a source of knowledge that records the evolution of software that's happened over time. And this source of knowledge is called our version control repository. So by mining the data that's already in our source control repositories, we could get some answers to the questions that we may have about technical debt. For example, this one. Where is the biggest return of investment from the cleanup effort? And this can be answered using a mechanism called hotspots. And they basically work like this. First, let's take every file in our repository and let's count the number of commits that touch each file. Then let's graph that, starting with the files with the most commits and going to the files with the least commits. And that's exactly what the author of this book did. So he analyzed the Erlang repository and he got the following result. The most of the development, most of the commits happened in only a handful of files. And there were lots and lots of files that were barely touched. So he ran the same analysis on the Ruby on Rails repository, and he got a strikingly similar result. So I was like, no way, that can't be a pattern that's recurring throughout the software projects. So I did some analysis on my own. I analyzed Apache Kafka, then I analyzed NSubstitute, I analyzed NUnit, Node@Time, I analyzed my own open source project, and then I analyzed one of the services I work on here in Motorola. And the results are very, very similar. So the most development happens in only a handful of files, and there are lots of files that aren't touched almost at all. So if we are looking for a place where we can make the biggest impact and have the biggest return of investment, the files on the right are an instant skip. We'd better focus on this part and pick several of the files that have the highest change frequency and focus our cleanup efforts there. And that's one part of a hotspot. And the second part is complexity. And typically, when we talk about complexity, we think about cyclomatic complexity, right? So for example, this is a flow that has a complexity, cyclomatic complexity of 3. And the number 3 is pretty significant. It means that we will need at most 3 tests to achieve a full branch coverage. However, cyclomatic complexity is kind of hard to extract from the code because we need some kind of parser for our programming language. And it's not perfect anyway. So for example, this is a piece of code that I would consider fairly complex, although Grzesiek would probably disagree with me. And it filters a collection over several criteria. However, most of the cyclomatic complexity analyzers will show the complexity of this code as 1. So knowing these two things, that cyclomatic complexity is hard to extract and it's still not perfect, we may pick another proxy for complexity, something that's easier to calculate and simpler, like lines of code or even indentation. And as a matter of fact, there is some research that shows that indentation is a really nice proxy for complexity. So we basically take a piece of code, count all of the indentations, and sum them up, and we get a number 15. And the number itself isn't really that significant, because if we used another coding style, the number would be 9. But as I said, we don't care about the exact number. If our coding style is consistent across the repository, we can use that to rank by complexity. In other words, I don't really care whether my manager is 57 and helper is 34, or manager is 43 and helper is 25. All I care about is that manager is more complex than helper. So having these two pieces of information, the change frequency and the complexity, we can try to visualize that or rank. So if we decide to visualize, we can represent the change frequency as a color and the complexity as a size of a circle. And by doing that for the whole repository, we get something like this. And here we can see that the manager CS is probably our top cleanup priority, because it is one of the biggest, the most complex files, and at the same time, it's one of the most frequently changed. All right, so even if we're still not sure if this is the right pick, we can take a look at the complexity trend. Because, remember, the source control repository holds all the versions of a given file. So we can calculate the complexity for each of the version and graph the complexity over time. Right? So here we can see that the file has received lots of commits. However, many of them were cleanups, and they lowered the complexity. So that might mean it's not the best candidate for cleanup right now. On the other hand, here we can see that this is a complexity trend with no complexity drops whatsoever, which means that it probably desperately needs to be cleaned up. And all of the stuff I told you can be scaled up to components. Because if we have some kind of component structure, for example, we have call processing component that talks to voice transmission component and uses the authentication component, this typically more or less translates to some kind of folder structure. So by aggregating these metrics on the level of folder, we can get hotspot map for our components. And here we can see that the call processing component is our top priority, the top hotspot. And it's mostly due to the voice transmission subcomponent that's here. So if we need to make a cleanup decision on the level of component, we can still do that to a degree. So far, you've probably noticed that this is an approach that does not give us definitive answers. It's not an algorithm or a formula that you put some numbers and get a straight single result. Rather, it delivers suspects, trends, rankings, and clues that aid our investigation and amplify our judgment, which is no surprise considering that this approach was born from forensic psychology. So, knowing that, we can try to ask another question, which is, does my architecture support the way my system evolves? And it should, by the way. And we can, to a degree, answer this question using a mechanism called change coupling. So let's say we have 3 files, helper, manager, and util, and 5 commits, C1, C2, C3, C4, and C5. And let's say that in that commit C1 touched manager and util, the commit C2 touched helper and util, and so on and so on. So what we can see here is that manager and util very often change together. As a matter of fact, manager changes with util in 100% of its commits. Okay, so the question that we need to ask ourselves now is, does it surprise me? Because sometimes it's okay. For example, here we have a rule builder class that changes together with a rule builder test class. And that seems pretty much okay because it's all natural for the tests to evolve together with the code, right? Here we have a tenant ID validation and request validation that change together often. And as you can see, they are part of the same component, which is probably okay as well, because according to one of the solid principles that's called common closure principle, classes that change together should be packaged together, and that's exactly the case here. However, this might be interesting. We have user repository and issue repository that's changed together very often. And users are something separate from issues, so why would it change together? So maybe there is some kind of duplicated, copy-pasted query building code that needs to be changed in both places. So that probably demands further investigation. And another example is something like this. We have the user repository that very often changes together with user controller, user service, user, and user DTO. However, as you can see, they are all in separate components. So this kind of violates the common closure principle because these files tend to change together and they are packaged separately. And this means that our system evolves along the use cases. However, it is structured by technical considerations, which means that each time we add or modify a use case, we will need to cross several component boundaries just to make our change, which may be a bit tiresome and troublesome. So this is an example of where our architecture works against the way our system evolves. So what can we do? Maybe we can take this architecture and change our primary division style from one based on technical considerations to one based on use cases. So that might mean, for example, picking all these files and packaging them together in users component. And by the way, if we one day need to break out a microservice that deals with user management, we can just break out this single component, maybe do some small changes in the code. Anyway, it should be easier. Okay, so the next question that our source control repositories can answer is who knows what? And we can answer that using a technique called knowledge maps. And here's how it works. Let's say we have 2 developers, Syed and Piotr, and we have a file called manager.cs that has the following history. Syed committed the initial version, then Piotr added feature A, then he added feature B, and then he added feature C, and then provided a bug fix for feature A. So from this history, it seems that the person that is most knowledgeable about this piece of code is Piotr, because he delivered the most changes. And by calculating these changes for every file, we can create a knowledge map where we can assign each file a de facto owner, which is a person that did the most changes. And you can use this knowledge map to answer several questions. For example, who is the domain expert? So for example, for this part of the code, the domain expert is probably Piotr, and even if he isn't, he probably knows who the domain expert is. So he is the primary point of contact. Another question we might answer is, what if a person leaves? So for example, let's say that Piotr leaves in 2 months. And we know that he is the owner of our top priority hotspot. So that might mean that we need to mitigate this by, for example, arranging some knowledge sharing or having him refactor this code before he leaves. Okay, so what if Piotr has already left? That means we have some kind of abandoned knowledge, 2 pieces of code that don't have the owner. So if we are planning for some work that touches these files or components, we might need to put off some extra time for refactoring and regression testing. And the last thing knowledge maps can tell us is diffusion of knowledge, which is a situation that happens when a file does not have a clear owner. For example, in a case where each of the developers only committed a fraction of the changes. And there is some research suggesting that files like that tend to attract more defects. And speaking about attracting more defects, can we measure that as well? Well, yes, to a degree. So for example, if we have some kind of standard commit message for bug fixes, we can treat it as a pattern and count this per file. So let's say we have a helper.cs file which has the following history. And it has 3 commits that look like bug fix commits, right? So we can count them and again either rank or visualize that. And we can see roughly which of the files attracts more commits. For example, this one. And if this is our top hotspot, we might use this information for further justification of the cleanup. So these are some of the basic techniques that Adam Thornhill came up with. There are really some more advanced techniques, but I wanted to show you some of the basic ones. So let's talk about tools. And there are a few tools that support this kind of analysis. And the first one is CodeScene, that is written by the author of the aforementioned book. And this is really a state-of-the-art piece of software for this kind of analysis. It is the most advanced that I know. It has the key personal metric, it has the abandoned code metric, the hotspot health, the interactive hotspot map with zooming capability, the visualization of change coupling, and so on and so on. So it's really, really advanced. The drawback is that it's not free. It's only free if you use it for a public Git repository. Other than that, you have to pay. Then there is another tool by the same author, and this one has a smaller feature set, and it's a console utility, and you have to compile it by hand if you want to use it. However, if you're not scared of compiling Clojure code, that may be a good fit for you. It's still pretty advanced, although it does not have the bells and whistles of this first tool. And then there is a tool that I started writing, and I called it nhotspot. So I started it to test and learn and practice about all of these techniques, or at least some of them. And for now, it's pretty bare bones. It just displays an HTML report, but it has some capabilities like it has hotspot ranking, it has knowledge ranking and contributions, it has coupling, change coupling measurements. So it has several features that can already be used in practice. Okay, so to summarize, your source control repository is a gold mine. That's what I believe. And you can use it to aid your investigation and to inform your decisions. Although it will not provide definitive answers, but suspects, trends, rankings, and clues that can aid your investigation and amplify your judgment. And I use these techniques in practice to refactor 2 of my open source projects to change the architecture and design. And I can only recommend them. I mean, the practice is not the projects, although the projects are needed as well. So a part of that, it installed in my head a question that I now try to keep asking myself every time I do something with software. Does my architecture support the way my system evolves? And this is a question that I would like to leave you with. Thank you. Questions?
Yeah, I mean, do you wonder why the files that are like modified by all developers in equal, like as you may see, like let's say have 4 developers and that all developers are modifying some file, and that file has most defects. So do you wonder why? Is it like a
just to set it straight, I didn't actually say that they have the most defects, but they attract more defects to that file that have clear ownership. So the justification that I heard is that there is no single mastermind behind the way the file or the component works. And this means that everyone that makes changes does so with incomplete knowledge. So if there was an owner, I could at least ask that person. And again, that's a rough estimation. It may be that all of these developers contacted one person that has all of the knowledge about this code, right? That's what I meant when I told that it aids investigation and does not speak the absolute truth. But that's something that can inform your decisions. For example, you may do some further investigation to check what's going on with this file. Is there anyone who really knows how it works?
I mean, it sounds strange because developers are fighting for for knowledge sharing. So like there shouldn't be any a star that a developer that knows the most about that file, because if he will leave, then he's living with the knowledge about the magic about that part of code. So that was what I was asking. Like this.
Yeah. I think I know what you mean. So my impression was, when I read about that there are conflicting forces in software development. And that's exactly what you said. So on one hand, it would be nice to have a single developer that knows everything about the file because he has a clear vision. On the other hand, if one person that knows everything leaves, we lose everything, right? So these are the conflicting forces that we need to balance somehow.
And there's additional thing, because if there's one person that has one vision about the file, let's say, some service, that he doesn't have another approaches how to extend that functionality. So it's even weirder for me to let's say have a person that is like a star for that that's the best developer for that file.
Remember that the statistic. So it's not an absolute truth that works in every situation.
I mean, I don't say that is like not true. That is like I don't understand that.
Yeah. So my thoughts on this were, I wondered about the same stuff. So my thoughts on this were that there are conflicting forces, and some of them work for us to some degree, and at the same time against us in another.
Thank you.
So sorry, no free lunch, right, or something like that. Okay. Do we have more time, or? All right. So thank you very much.